Hello everyone, I'm Joaquin Gajardo from ETH Zurich, presenting our work Wheat3DGS in-field 3D reconstruction, instance segmentation, and phenotyping of wheat heads with Gaussian splatting. High-throughput field phenotyping of wheat is crucial for sustainable crop production, but faces several challenges such as dense canopy structures with heavy occlusions, complex morphology of wheat heads, and costly equipment. Current methods have significant limitations. Manual measurements are labor-intensive and subjective, laser scanning is costly and time-consuming, and multi-view stereo struggles with fine details and occlusions. Furthermore, there's currently no straightforward way of performing 3D instance segmentation of plant organs across several plants. Our approach addresses these challenges using 3D Gaussian splatting with just 30 multi-view images, enabling automated and affordable measurement of key wheat head traits at scale. Our work builds upon recent advances in 3D computer vision and their application to agriculture. Neural radiance fields, or NERS for short, have revolutionized the field by using a neural network to implicitly learn the appearance and geometry of a scene captured with multi-view images. Follow-up methods like Instant NGP dramatically reduce training times using auxiliary data structures. More recently, 3D Gaussian splatting has emerged as a powerful alternative, using explicit 3D Gaussian primitives and fast rasterization to achieve real-time rendering while maintaining reconstruction quality. Nerf-based methods have been rapidly applied in agriculture for tasks such as fruit counting, 3D segmentation, and plant phenotyping, but mostly in controlled environments. While 3D Gaussian splatting has only been explored so far for 3D reconstruction at the single plant level. Our approach extends these foundations to address the more challenging problem of 3D instance segmentation of wheat heads in dense outdoor wheat fields. Our method starts by reconstructing a wheat field with 3D Gaussian splatting from multi-view images, from which our task is to identify and extract individual wheat heads. For this, we use 2D wheat head detections from a pre-trained object detector and the Segment Anything model to generate precise segmentation masks across different views. The key challenge is that we don't know which wheat head in one view corresponds to which in other views or in 3D. Building upon FlashSplat framework for lifting 2D masks to 3D, we develop a novel match and fine-tune strategy. For each wheat head, we lift an initial 2D mask to 3D by annotating Gaussians belonging to it. We then render this 3D segmentation in other views and find matching 2D masks with high overlap, which we then use to refine the 3D segmentation. This iterative approach gradually builds up confidence in which Gaussians belong to each wheat head, despite inconsistent views, enabling us to detect and segment hundreds of individual wheat head instances per plot. We collected data from 7 outdoor wheat plots containing 6 rows of different wheat varieties using ETH Zurich's field phenotyping platform. For each plot, we captured 36 multi-view images and used 3 geocoded markers for alignment and scale determination. For ground truth validation, we perform high-resolution terrestrial laser scanning with 19 register scans, providing a reference dataset for evaluating our reconstruction and measurement accuracy. Our results suggest that 3D Gaussian splatting significantly outperforms Nerf-based methods in reconstruction quality with better structural similarity, peak signal-to-noise ratio, and perceptual metric scores. The visual comparison highlights the differences in reconstructing details. 3D Gaussian splatting captures fine-grained structures like wheat head awns that Nerf-based methods miss or blur. This superior reconstruction quality is critical for accurate segmentation and trait measurement in subsequent steps. We tested different 2D detection methods and chose a combination of YOLO and the Segment Anything model for its higher quality detections compared to the state-of-the-art foundation model grounded SAM with the prompt wheat head. To evaluate our 3D wheat head instance segmentation approach, we projected the segmented 3D instances onto 2D test views and compared them with manually annotated ground truth masks. Our method effectively incorporates partial information from multiple views, enabling it to accurately detect a significantly larger number of wheat heads than competing approaches. We validated the geometric accuracy of our approach by comparing our extracted wheathead instances to their matches in terrestrial laser scans and multi-view stereo point clouds in terms of length, width, and volume. We achieved low per instance errors, particularly for length and width, and our results are comparable to those obtained with high-resolution structural light scanners at a fraction of the cost. Most importantly, an analysis of variance at the row level showed that our measurements provide strong discriminative power between different wheathead varieties, sometimes outperforming the reference terrestrial laser scan measurements. Our method does not come without limitations. Efficiency can be improved, and there are several common failure cases, including incorrect reconstruction at lower canopy levels, errors in instance segmentation, and ambiguous geometry reconstruction with the strongly expressed ons. Future work will focus on improving efficiency for broader adoption and introducing shape priors to improve volume estimation, which show higher uncertainty than length and width measurements. In conclusion, Wheat3DGS enables precise 3D reconstruction, instance segmentation, and affordable morphological measurement of wheatheads in complex field conditions. Our work provides a major step for automated crop phenotyping on new challenging traits. Our paper, code, and dataset are available on the project website, accessible through this QR code. Thank you for your attention.